कुछ प्रॉब्लम आ रहा है क्या पीपीटी वीडियोस में? No, 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 sir. Actually, the first of all, the anchor will introduce you. Then I'll stop the sharing my PPT, and then you can start sharing yours. Yes, sir. Yes. Hello. No, no. You will share your PPT after the introduction, sir. Okay. Yes, sir. Yes, sir. You have stopped actually already. So I have shared. Are you able to see my that poster? Okay. Okay. That's fine. So I just inform you, I just inform you, and then I request you to start the introduction and you share. Okay? Okay. Present, they will introduce about your introduction which you have shared to us. Yeah, yeah. Okay, okay, okay. Sure, sir, sure, sir. Okay. The amount of. Okay, okay. No, 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 no. We will not mention that, sir. Yes, sir. Yes, sir. Okay, okay. जी जी अरे धीरे रखो ना वही साइड तो खींच लेगा ना हेलो हाँ राजवीर उनके इंट्रोडक्शन में उनका जो फंडेड प्रोजेक्ट है ना उसका अमाउंट तो मेंशन नहीं किया है ना हाँ कोई सा भी प्रोजेक्ट का अमाउंट तो मेंशन नहीं किया है ना हाँ वो ठीक है अमाउंट 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 कितने हजार कितने करोड़ कितना लाख ये तो नहीं हाँ बस बस यही पूछना था और कुछ नहीं ठीक है ओके नहीं अभी नहीं अभी नहीं अभी जरूर करूँगी यार जो मैं पूछा 5 मिनट बाद स्टार्ट करते हैं अब मेरे को छुट्टी करवाना पड़ेगा सबसे क्या सर ज्वाइन करवाना पड़ेगा सबसे भैया ज्वाइन नहीं हो रहे पार्टिसिपेंट 24 पार्टिसिपेंट नहीं क्या पता एक तो सर वो मैसेज डालने के बावजूद स्क्रीनशॉट डाल दिया है इसका तूने देखा है ना ठीक है मैं आता हूँ हाँ चल रहा है ना कोई हाँ चल ठीक है अरे तो मोबाइल छोड़ गया रे तेरा मोबाइल मेरे को भी बना दो बस 5 मिनट से मैं फिर हाँ वॉइसेस हाँ हाँ आराम से बना नहीं नहीं तो उनको ना आप मत करो अभी मैं कर लूंगा ये सेशन तो मेरे को भी बना देना हाँ 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 आप ज्वाइन कर लिए क्या कर लिए क्या ज्वाइन हाँ कर लिए ठीक है रहने तो ऐसा कुछ नहीं है 5 बजे तुम लैपटॉप से जाओ हाँ 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 मोबाइल छोड़ के कोई है क्या क्लासेस में यहाँ पे बैठे हैं क्या कल से में अपने पता नहीं चलिए यहाँ पे ज्वाइन करो Very good. Done. Rajveer? Hello, Rajveer?
Yes, sir.
Rajveer, you can start the session.
Okay, sir. Good afternoon, everyone. I hope you are all doing well. I, Rajvi Chaudhary, student of Electronics and Communication. Welcome to the first session of last day of Atal Online Faculty Development Program on recent trends in semiconductor device, modeling, and circuit technology, a field that play a crucial role in shaping modern technology and innovation. We are honored to have Dr. Mahendra Vucha, an expert speaker from Aero Electronics, Bangalore. Dr. Mahendra Vucha is a highly accomplished associate design engineer, technology, trainer, and innovation consultant with over 10 years of academic experience and 5 years in the industry. He earned his PhD in VLSI, Heterogeneous Computing System Design, from the NIT Bhopal. Dr. Vucha has made outstanding contribution to the field of technology and innovation. He has led multiple research projects, including the design of SCUR multimedia application for heterogeneous multi-code platforms. He has played a key role in establishment innovation leadership center such as Atal Community Innovation Center funded by the government of India. He is the author of 25 research articles. He has been recognized an innovation ambassador by the Ministry of Education, Government of India. Recently, working with Aero Electronics Bangalore, Dr. Vicha brings an extensive expertise in semiconductor devices, circuit technology, and system design to this session. Without further delays, I invite our expert speaker, Dr. Mahendra Vucha, to begin this session. Sir, over to you.
Yeah, thank you for the introduction. Yeah, myself, Dr. Mahendra Vucha. And today I'm going to give you some insights about SOC design. Let me share my screen.
130 नहीं 187 और 140 और 124 तुम्हें आया जब तो बता देता ना टीचर को अच्छा बाकी चैनलों में काम भी है 137 140 140 मैं रेंज में आऊं क्या लिखी वाला है ना काम ही कर रहा हूं मैं तो लगाऊंगा अभी अटेंडेंस तो मैं सारा में लगा दूंगा है ना ओके ओके Mahendra sir, you can share this screen.
Yeah, I'm sharing my screen. Yeah. Can you see my screen? Yeah, can you see my screen?
Yes, sir.
Yeah, I'm audible. I'm audible.
Yes, sir. You are audible, sir.
Yeah, thank you. Very good afternoon. This is Mahendra. Actually, I am working as a associate design engineer at Aerotronics, and also I have implemented till now 2 associates. That means I am the part of the associate design team, and we have processed 2 designs. So with that experience, I am here to give you insights of associate design, that is practical implementation approach to you. That is for the academia people, where you can do the research and further enhancements to the associate design. Is my voice is clear? And do you want me to increase my speed?
Sir, it is comfortable.
Yeah, thank you. Now these are the presentation outlines. Initially, I'll give you introduction to the associate design, and then various system implementation approaches, and we discuss the implementation flow, and then challenges what we face, and also some use cases I will show you, and then I will give you some of the research fields where you can start your research if you would like to do the research in associate design. Yeah, coming to the introduction to the SOC, this is the very important how revolution happened in the technology towards the SOC. Now, if you look at this slide here, you can see computing architectures, communication interfacing, and operating system applications. These are the well-known technologies what we hear in the day-to-day life. Coming to the computing architectures, in general, we use the CPUs or GPUs. GPU here, graphic processing unit, and microcontrollers and memories. These are the things what you can see in most of the computer systems. Now we can treat this as the hardware. And coming to the next kind of hardware is that is communication interface. That is the LAN, WAN, Bluetooth, Wi-Fi, cellular communication, and the GPS. These are the various communication mediums, or I can say interfaces, which can be used to communicate with the hardware or computing architectures. Now, these should be the hardware architecture for any system. Now, coming to the next level of system design, operating system and applications. Actually, every general purpose computer system will have the operating systems, and we do develop the software that is called application software and execute in the operating system. Now that's how we are implementing
तो फिर घर पे एक सेशन का वो वही रहेगा फिर दूसरा 5G से कौन है सारा 5G तो अभी उससे ले जाना साथ में कि वो बाद में आएगा ऐसा दिक्कत नहीं होगा कुछ नहीं मैं कह रहा हूँ तेरे नेट से कनेक्ट कर दूँ ना पहले मैं तभी लिया तेरा हॉटस्पॉट ऑन करना
and then produce the final results what we want. Now that is how we are doing. That is what I have kept here as the introduction. Here we have the computing architectures, communication applications can be developed in the form of the software, and that software will be executed in hardware. Now whenever we do this process, process, we have the key challenges. Now here, the real-time challenges what we face is flexibility. That is, whenever I want to change the hardware, then there is the possibility to change the architecture. That is what the flexibility. Or if I want to change the application, then I have to execute that application on the same hardware. Okay, such type of flexibility is very required. That means we require the flexibility in hardware and also application conditions. Now coming to another challenge is that is speed, and we need the system to be executing the tasks whatever we want at the expected speed. This is another challenge. Meeting the speed is another challenge. Coming to the performance, yeah, performance is considered. See, this speed is how fast it is doing, but how effectively it is doing is also important. Now, finally, efficiency. Efficiency is how much power is consumed and what is the area. This all comes under the efficiency quality. Now, these are the various challenges. There are many challenges, but I have kept a few challenges which are very good devices. That is what we can say sensors and actuators. Sensors will detect the real-time environment, and the actuators will control the real-time environment. Now, these are the various components what we could see in the hardware part of the system. Right. As I said, system on chip is software, hardware, and software integrated together. So now we have seen the hardware will have digital, analog, and I/O. Coming to the software is having the system software. That is what the drivers for all the hardware integrations, device drivers. I hope you might have heard the word device drivers. So that is what the system software I can say here, and also kind of real-time operating systems comes under the system hardware and application hardware. Whatever specific tasks we need to perform, that can be taken as application software. So here we do develop the system software as well application software both, and then integrating system whatever developed by using the hardware. That means we are embedding the software into a customized hardware. That complete thing will be called as system on chip. Right? That is what putting the system onto a chip. Right? That requires this process: hardware integration and also software development, and then integrating both of them and making that as the final package. That means packaging will have signal interface and then integration to complete the system on a single chip. Right? This is how we can transform the system specifications into a chip. You can call that as system on chip. Yeah, now let us go to the next, the abstraction levels. Now you can look at this abstraction level. That means here in this abstraction levels stage, I would like to discuss about how the process, whatever we have seen here, the process converting the system into a chip. Okay, that process can be taken in stages, various stages. Now here we can convert the system into a chip in three stages. That is first architecture. That means, as I said, at the very first stage, what we do capture the specifications of the system, and we have to convert that specifications into a systematic model. That is what we can call architecture. Actually, the architecture what they do, that uh, converts the system specifications into the hardware and software models. Hardware and software. That is what I can say here. Describe system level specifications and develop functional description for the system specifications. That means after developing the functional description, then we can divide them into a hardware and software, as I said here, right? As I said here, the hardware and software. So the functional units can be further divided into the hardware and software. Hardware units can be implemented by using the hardware implementation mechanism, and software can be developed by using the software development side. That already you met out studied, but otherwise you can just go through. Okay, so that is the standard process we do follow. But here the hardware implementation is customized hardware implementation. For the hardware implementation, we do follow specific stages here. So at the very first stage, what we do develop the architecture for the system. That system architecture will have both hardware and software, right? And that can be described, means the function description of the system can be described by using the C++, system C, and Simulink Maker. There are many tools are available, and we can use those softwares and tools to convert the system level specifications into functional descriptions. After converting the functional level descriptions, we do divide that functional level descriptions into the hardware and software. So hardware part will have the RTL design stage. That means here, I hope everyone knows what is RTL. That is the HDL code, writing the HDL code. That is what register transfer level. Register transfer level, where we do write HDL code. That means we do convert the behavior of a system into a hardware. That is what you might have done in the academics. Even in industry also we do the same, but here in the academics you may have the one course hardware description language course, that is HDL are very normal, and that can be used for converting your description or system description into a hardware. For this, one example I will tell you. You might have seen the addition operation in general addition operation, but in the studies you might have seen half adder, full adder, multiplexer. These all are the various hardwares, right? If I take the half adder is the hardware structure for performing the addition operation. Same here, the RTL design, what they do, your system specifications are converted into a hardware. That is what we can call netlist, right? In the terminology, we can call that as netlist. We do write the RTL code and then convert that RTL code into a netlist, where netlist is the interconnection of the logic gates. I hope you know, right? Now coming to the physical design. See, after converting your specifications into a hardware, we need to place that hardware into a floor plan area. That means now, as I said, system can be converted into a chip. System is having the system is having the specification, but system is having the boundaries. So whatever hardware you have developed by using the RTL design states, those hardware should be kept into a small area, right? That is what called physical design, where what we do, take the RTL and the library of variable logic gates. As I said, the RTL is converted into the gate level netlist. All those gate level netlists are defined into a particular area, that is chip area, I can say chip area, and then we can is what wire them. That means define placement for logic gates and then wire them together, and then we do verify the design requirements. As I said, the system will have some specific functionality. After creating the hardware for the specific functionality of the system, we need to again verify whether the hardware whatever we have created is working fine or not, right? That is what we need to do. That's why the SOC design will have three kinds of abstraction levels. That is architecture, where we do convert the system specifications into the functional blocks. I can say simple, instead of functional description, I can say functional blocks, and those functional blocks are
Hey
implemented by
boy,
your hardware and software.
Ray
So we do,
Matka.
for the implementation of hardware, we
Hello,
do
hello.
follow the RTL design, where we do write the HDL code for the description of the functional blocks, and then convert them into the gate level netlist. After converting them into the gate level netlist, we can uh, put them on the chip, right? We can call that process of putting the RTL, not RTL, gate level netlist into a fixed area called as physical design. Again, the physical design is one kind of big process, right? That is not required here at this point. If you want, you can browse it. Most of the information is available. And then we do verify whether this hardware, whatever is placed into a single chip area, is working as per the system requirement or not. After that, we do go for manufacturing architecture. Now, these are the three stages of abstractions what we do follow to design the SOC. Apart from this, I have mentioned here one more IP based designs. Now, here for everything, okay, there is no need of writing the RTL code. Why? Because if you start writing the RTL code for everything from the scratch, that takes a lot of time. As I said, there is one more challenge, that is time to market. That means we need to develop the product as early as possible in order to release into the market. Otherwise, your competitors will capture the market. So, in order to do every time the process, what they do, they can create the IPs, intellectual properties, and we can use those intellectual properties ready-made. Okay, in the stage of RTL design. The RTL designs, either we can write the HDL code from the scratch, otherwise we can use the IP-based designs, right? So here the IPs, intellectual properties, are available in three forms. One is hard IP. Hard IP means complete optimization is done, and that black box. That means we cannot touch that anymore. Directly we can use that in our design. That is what, okay, most of the processors, memories, and some of the communication interfaces will have the hard IPs. So we can use them directly. Next kind of IP is firm. Okay, so here we can have the synthesized netlist. That means gate level netlist is available. Gate level netlist, we can integrate that gate level netlist as per our requirement. The last one is soft IP. Soft IP is RTL code. RTL code means English letters. That is HDL code. That HDL code can be synthesized to convert into the gate level netlist and then used in our design. That means the RTL design process is can be done from the scratch. Otherwise, we can use the ready-made IPs which are available in the market. Right? That again, makes the lot of difference here. If you use the IPs directly, then we can save the lot of time, right, to release the product into the market, right? So in general, these are the three stages where RTL design can be. Now let us look at this abstraction levels in the form of signal flow graph. Here you can see here RTL design uh, is implemented in this way. Here I have shown this as implementation flow. Here, as I said, the system specifications are captured, and those system specifications can be used to develop the architecture, system architecture, and also see while this, after designing system architecture, we need to test it as to verify its functionality. So for that also we need to develop the uh, verification patterns, verification methodology. So that means that will have the test patterns. What are the inputs we need to give, and then what are the outputs expected, and then we do give the inputs and then verify whether the expected outputs are achieved or not. Now that is what we can call testing, right? Functional testing is there, physical testing is there, right? But here in this slide I am mentioning only functional testing. Here what do we do? From the specifications we can develop the verification methodology also, or testing methodology. The testing methodology will have the test patterns, right? And those test patterns can be used for verifying the functionality of the system. So here, after capturing specifications, what we do develop the system architecture, and then we do partition the system architecture into a hardware and software. So hardware can be implemented here. Hardware design can be implemented by writing HDL code, or some of the analog blocks need to be integrated. So analog and RF blocks will be available as IPs, or also you can design that separately by using the analog tools are there. Analog design tools are there, right? We can use them separately and then integrate all of them together, right? So that will give us the netlist, complete netlist, which can be manufactured, right? Similarly, whenever we do partition the system into the hardware, this is the process of converting the hardware and then integrating. Now here there is another process. Here we need to develop the software also in parallel, right? In parallel, and also we need to test the developed hardware and then software at the development stage also, right? So here we do develop the test modules also, right? So this is the complete the parallel stages, right? Developing the hardware, developing the software, and also developing the testing methods, and also providing the uh, available IPs to enhance the design process, right? All those things will happen here parallelly, right? And this hardware stage gives the netlist, that is the gate level connections of the design, and this gives us the embedded software. So this netlist and embedded software is integrated, and then the SoC is manufactured. So SoC is manufactured first, and then embedded software is embedded into the chip. Right? Now this is the system integration and verification in real environment. After developing the system, we do use the testing modules to test that in environment. Now this is the complete implementation flow what we do follow in the industry, right? The same cannot be possible to do in the academics, but here in the industry we do start from the capturing the system specifications to this. Here in these various stages, there are a lot of engineers involved. Total for implementing this for a single chip, we need minimum 500 engineers at various stages, right? For at least 6 months to 1 year. That is, it depends on the complexity, right? My role is actually in the industry. What I do is I do work in this area, right? Integration of hardware, and then developing the physical structure for it. Now in this area I do work, but here in the broad aspects I can say here there are engineers, application engineers, and then architects, again RTL design engineers, right? And then physical design engineers, verification engineers, right? Design for test, DFT engineers to develop these test patterns, and then to verify the net list, there are some engineers, right? That is net list verification engineers. Again, software, there will be some teams for the software development. Now, this is not done by a single person, but it can be done by multiple persons. But everyone follows the same sequence of implementation flow, starting from the specification, capturing to the system integration, and then verification in the real-time environment. Now, this complete takes minimum 6 months to 1 year in real time. Yeah, this is the SOC design implementation flow, and you might have seen some of the flows in our academics. That is ASIC flow, ASIC design flow, right? And VLSI design flow. Similarly, here this is the SOC design flow where we can have the hardware and then software is going in parallel. But in the ASIC design flow, it may not happen. It is straightforward developing the hardware to a system specifications. But here there is need of the developing the software also in order to make that as a system on chip. System on chip is nothing but hardware plus embedded software. Okay. Any query here?
Yes, sir.
Yeah, any query? I can proceed further.
Yes, sir. You can proceed, please, sir.
Yeah. Now coming to the challenges, as I said, now this is the implementation flow. It looks like very simple and systematic, but there are many challenges behind this. Right now, here I kept a few challenges. SOC. If I start developing the SOC for I can say for data analytics, right? So again, some other requirement will come. They need some extra feature in that. If you want to add some extra feature, again we need to work on it, right? So here the biggest challenge is the functionality and complexity of SOC is increasing day by day. So we need to develop the SOCs in that required rate. That means the speed, mainly speed is very important. Now here in the SOC, biggest advantage is speed. Why? Because all the chips are available very near to each other. So that reduces a lot of communication time. Here most of the time wasted for the computation is the communication. That means data reading from the memory and then storing back. This takes a lot of time. If everything is available nearby, then speed will be enhanced. If you start enhancing the speed, again some other application will come at required at high speed. Nowadays, the biggest challenge of the chip industry is developing the chips to support the artificial intelligence applications. Artificial intelligence applications require very high speed, right? That is as speed as human brain. That much speed we need to achieve. That is the biggest challenge what we are facing nowadays. Now that is one challenge. Second challenge is time to market. Time to market is becoming very low nowadays. Very low in the sense they need the product within a 3 months or 6 months, but that is highly impossible. But that's why this IPs has come up. Instead of writing the HDL code, what they are doing, they are integrating the IPs and then testing the functionality. After that, going for physical implementation and then manufacturing and giving to the customers. Right? That is how we are achieving the time to market. Even that is becoming critical nowadays. Next one is design partitioning. As I said, the system specifications are captured and then kept in the architecture. Right? After that, we need to divide which part of the system is implemented using the hardware, which part can be implemented using the hardware. Now that is again biggest challenge. Why? Because I hope you already know. Otherwise, I will tell you one scenario here. Always hardware implementation of the behavior is having high speed than software implementation of the application. For this best example is, if I want to perform the addition operation, writing the program to perform the addition in general purpose computer system takes a lot of time. Instead of if you use the half adder or full adder, that takes the less time. That means I can say here the hardware implementation is faster than the software implementation. But here we need to take which blocks need to be developed by using the hardware process, which part need to be taken care by the software process. So that partitioning is very difficult nowadays, right? Anyway, that can be achieved, but there is challenge to convert which portion of the system is implemented on the hardware, which portion of the system is implemented through the software. Right. Next is the third party IP integrations. Nowadays, if I am the engineer in a company, if that company is not having particular IP, right? Now let us take one camera interfacing IP is not there, but I want to develop the system on chip for camera interfacing application, but I don't have the IP, so I have to take that IP from the other company. So now what I do, I have to take that from the other company. I have to integrate that into my model. Now that is again biggest challenge. If I don't want to take that IP from the other company, if I want to develop by myself, then most of time will go for implementation of that IP itself. So here the biggest challenge is third-party IP integration, right? So next one is mixed signal verification and debugging. Nowadays, most of the data processing is happening not only digital, not only analog. It is happening in both ways, analog and digital. So the mixed signal process is very challenging. For that, we need the separate kind of verification and debugging methodology. That is also another challenge. Next is meeting the speed requirement. Here, time to market is one requirement. Another one is speed. At what speed this chip should run. That is what biggest challenge. For that, we do follow the parallel processing concepts. Right? I hope everyone knows what is parallel processing. Multiple tasks are processed parallelly. Right? But we need to develop the hardware that supports the parallel processing to meet the speed requirements. Finally, the power is very challenging, right? Power is very challenging. Every chip requires low power. Why? Because if the chip is consuming the less power, then automatically battery backup will be more. So here, everyone expects less power consumed chips. If I want to develop the less power consumed chips, then I have to use multi voltages. Multi voltage in the sense, now CPU works at 1.8 volt. Now communication bus may work at 0.9 volt. Another one will work at it's right 0.6 volts. Right. Another module may work at 1.1 volts. Like that. If I make like that, one module at one power, another module at another power like that, then there is chance of optimizing the voltage. Now that is the technique. What we do, low power technique, right? where we can use the multi voltages. Whenever you started using the multi voltages, then system complexity again increases. Why? Because we need to manage the voltage also to various blocks. That requires again additional architectures. Right? These all are the various real-time challenges what we do face in the industry. Right now, I'm working on this one, multi voltages. Actually, now for my current projects, we are implementing this multi voltages. That requires again a lot of understandings, and then bringing the right voltage to the right block. Now these all are the real-time challenges that brings the complexity to the again to the SOC. This side. Yeah. Now these are the various challenges what we do face. These are the major challenges I kept. There are many other challenges, right? That we can discuss in the future whenever we have another time to meet. Now coming to the classes of platforms, as I said, particular SOC cannot satisfy all the requirements. So we can, based on the application requirements, we can develop the SOCs. That is what I can say here. Classes of platforms, right? Here we can develop the complete application platform. That means SOC for the dedicated application. That is what full application platform, where hardware modules integrated through bus and the layers of firmware and driver software to create the application. That means here the hardware is created, and then we do have the software and the driver softwares to create the applications. Now, next one is process entering. See here, this is the in general platform, I can say. Now, whenever you want high speed, then we need to make the processor also high speed processor, right? That means we need to design the hardware with high speed process, right? Where RTOS kernels are made available through the library, so that based on the our applications, we can use the features of the RTOS kernels, right? So complete RTOS is not required. Few of the features of the RTOS can be integrated into a hardware, so that that can be used for the real-time applications. If you need the high-speed computation, then process entering platforms are required. But if you want the communication is most important, there we do work on the communication specific platform. That means we do develop the SOCs where communication media is optimized. Communication media is optimized. That means where data processing takes, and not data processing takes, data communication takes the major part, right? That means I can say network on chip, or networking process requires this communication specific platforms. Whenever it comes to the multimedia requires process centric platform. That means processor centric SOCs, right? Here it requires the network applications requires communicate specific platforms. Similarly, there are some applications which can be enhanced, or features of the system can be enhanced immediately with no time in the sense within a month, I can say, right? Where we need some flexibility in the hardware, where we need this some flexibility in the hardware, where we can use the configurable platforms. That means where the FPGA is integrated to a SOC. That means SOC will have the fixed hardware and also a flexible hardware called FPGA core. FPGA core. Actually, this is the my research platform. Actually, where I have done my PhD thesis on this transferable platforms. I have done my PhD thesis, where we will integrate the FPGA with the specific hardware, so that we can bring the reconfigurable facility to the SOC. Whereas some of the tasks are created on the hardware immediately. That means reconfiguration techniques can be applied, so that we can bring up the extra features to the hardware platform of the SOC. Right. For that, we need we have another kind of SOC platform, that is what configurable platform. Whereas we need the multi-processing. Nowadays AI demanding parallel processing. So whenever we wanted the parallel processing, we need multi-processors are integrated into a hardware part of the SOC. So if you do that, we can call that as MPs SOC. That means multi-processor system on chips. Now this is also another kind of platform. So here these are the various kinds of platforms. That means various types of SOCs can be designed based on the application requirements. Right now, here what I would like to tell you is the process is same. Whatever we have seen the implementation flow, this implementation flow is same. Only difference here it comes is here the optimization. In this case, we do give the equal optimization for all the functional blocks. But here, whenever it comes to here, it is computing optimization is required here. Here, communication optimization is required here. Here, the feature enhancements need to be done immediately. Here, we need the parallel process. So, based on the requirement, we can change the hardware portion. That means here we can change so that we can bring up the more IPs. Otherwise, we can, if there is no IP available, ready-made IP is available, then we can start doing from the scratch. That is what by writing HDL programming, all those things we can do, right? That here this part will change based on the platform requirements. So in general, these are the 5 classes of platforms. Now there is one more class of platform is coming, and that is called multi-processor programmable SoC. Multi-processor and then programmable SoC, right? Now these are the various characteristics. Already we have discussed it at the very starting itself: speed, flexibility, performance, and efficiency. These are the various characteristics every SoC design expects. That means SoC will have high speed and also flexible enough, and also should perform the tasks at real-time requirements, and should have the less power consumption. That is what the efficiency. So high speed, flexible enough, and meet the real-time requirements. That is what the performance, and also consume the less power. Now these are the various characteristics, and also I can say these are the challenges. Right? Meeting these is the challenge, and SOC expects these characteristics, and meeting these characteristics is challenge. Right? Okay. Abhishek, how much time I have?
Yes, sir.
How much time I have? I think.
Sir, we can finish in 5-10 minutes.
Okay. 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 Now, till now we have discussed about the SOC design. Now let us understand where to use these kind of SOC designs. Now, here I kept I am showing you one use case, that is AI specific use cases. That means artificial intelligence. How artificial intelligence can utilize the SOCs. Now here you can see there are 3 terminologies I introduced here. One is edge computing. The edge computing is nothing but the computing the data, right? Computing data. Nowadays you are seeing most of the phones and enterprises, everything is becoming as IoT based. Am I right? IoT sensors are integrated everywhere. But after the IoT network, IoT will have this set of sensors. Set of sensors. That means all sensors collect the real-time data. There is the need of processing that capture data at the enterprise level itself. Right? That is what we call edge computing. Right? In order to process the data in the real scenario, we need a computing platform. Right? The hardware computing platform where we can use the SOCs. SOCs nowadays mostly used for this edge computing. Right? Where take the data, analyze it itself, and then process. Through this, what we do, we can reduce the latency and make applications more energy efficient. Instead of carrying whatever data is captured and replace the central, that is in some cloud, right? So carrying the data to that point is not required. They themselves can associate where the computation. Example, another one, the research is happening on autonomous. In the sense, autonomous vehicle should be capable to react to the analysis as able to capture and process a large amount of right? Real-time database as quick as possible, like right? That means it should interpret the data from the campus and also process it. So that it's around a way similar to human. How can right? Does it drive the car? How effectively we do we do the breaks and let's all these things that much effectively that should work, right. Yeah, autonomous vehicles that will be completely relying on the chip and the algorithm which is running in the chip, right. So let's take one example of traffic light, right. I want to autonomous vehicle to stop at the traffic signal. What it has to do, they have to get the light, right? Then position of the other cars nearby, and also identify condition of the vehicle at the instant of time, and then give the key information, safe operation to stop, right. That much efficiency is required. I can say accuracy is required. To get that much accuracy, we need the computing software that should work at a very high speed. Right? As I said, the SOC is very high speed because of what the hardware are integrated on the rear. Right? That is why this is one example where SOC can be used. Now coming to the robot, nowadays robotics also becoming as human beings. Right? That means in the future, how human being behaves in the same way robot also can behave. But again, the high speed fix. High speed fix is again challenging, right? To design SOC for the robots. Right. The various use cases what we can analyze before design the SOC. Here I can say the SOCs are a suitable thing for this kind of use case. Not general purpose processor cannot serve this process. Right. This specific system is required. Right. So that's how the SOCs are coming up. So in the future, not in the future, now we are starting to work on AI SOCs. SOCs which can support the AI. Right. That is what they require. And this is the open area for the research also. But I can provide some of the research areas. Here in this presentation, I hope most of the audience are faculty and students. Now look at this research field here. As I said, the computation is required. That is what parallel processing, all this is required. In order to meet the real-time requirement, real-time requirement is artificial intelligence, more about artificial intelligence, right? And we need to service our research to artificial intelligence. That requires a data fabric. Data fabric is nothing but CPU, automatic logic units, memory, etc. Working on this. Also communication protocols, on-chip bus communication protocols, AIEA, AMA, bus protocols are there from the ARM processor, ARM company. Like that, there are many on-chip bus architectures required. SPI bus is there. But these are very old buses, but nowadays we need high-speed communication protocols to work on chip. The communication and computing units, that is what audio and graphic processing units we have seen. Your laptop will have the CPU and also graphic card. Am I right? What is the laptop nowadays having a graphic cards? Right. So there is a lot of chips for audio processing because AI require the voice. Right. And also that should visualize the real things. That graphic processing is required. Right. Audio processing is required. Right. There is no area to develop the data fabrics. Say process audio processing, graphic processing, or at least some portion of the audio processing unit. Right. Now this is another research area where you can work. Coming to the peripheral. Nowadays we have the sensor and actuators, independent sensors and actuators. But if you are able to build up the sensors and actuators, it can be represented on hardware. Right? That again brings the value of this research. in associates and concepts as a because design can be one of the research area where you can work. Like concept architects. Now, if you see, it's computing example. There, we need the processing and also communicating with other devices. Data processing and communicating with other devices. Since there we kind of process network process is required. So there are also having the other components required, like system on chip. All of the network concepts also can work on the network concepts. Finally, I can say power delivery network architecture. So as I said, in order to bring the efficiency, power efficiency, especially the SoCs, we need to work with multi voltages. And whenever there are multi voltages, then there is need a power delivery network. Right? Multi voltage power delivery network. Means you could say single voltage, but the single voltage can be split into multiple voltages and also bring that voltage to the required block. Okay. Now this can be done. One of the one of the research area where you can work. There are few research areas. So okay, I just I'm looking up here on. Now again, each research field is having the sub research fields. But in general, like I can say in the explosive design, now the enhancing required these fields. That is what specific here. You can take these requirements as research. Okay. Now with this, I can stop the presentation, and if you have any queries, I am available to take queries.
Thank you, sir. Thank you so much. I think one very discipline that is how to be with the issues SSOC.
As I said, see, thermal is that is kind of young generation. Correct. So here it is whenever the power dissipation is more. Right. So when the power dissipation and multi voltages. That is why the concept has come up multi voltage domains. So if you use the right voltage, then we can minimize the power dissipation. And here another challenge with SOC is the speed is the high speed of computing. When speed increases, automatically power consumption is more. Power consumption is more. That normal comes into the picture. Right. So in that case, you need to use the right voltage at the right speed. That's why this multi voltage concept is coming. The multi voltage concept nowadays one of the technique can be used to minimize the thermal effect.
Okay. Yes, sir. I'll share your contact and ID with you, sir.
I will give another email ID and then consider the office email ID.
Yes, sir. Sure.
Can you see my screen?
Yes, sir.
Yeah, here I will type program.
Even if possible, I if possible for this ability, then when you are query or any kind of proposal or the collaboration they want to do with you, that will be much better to contact directly.
Sure.
Thank you so much, sir.
And if you want, okay, you can
Yes, sir.
don't use my official email ID because you cannot.
Of course, sir. Yes, I know that, sir.
Yeah.
Yes, sir.
And I will confirm that is please come down.
Yes,
So I hope this session given you the basic knowledge of SOC. I don't think they gave you everything, but I have given you what is SOC, what is the SOC design flow, and where are the challenges and the research fields to work on.
Yes, sir. Thank you so much, sir. And I'm very thankful on behalf of our participants and all institutes to share your knowledge with us, to spare time for us. Thank you so much, sir.
Yeah, thank you.
Yes, sir. Yes.